slides are similar to last presentations, so I'll go through them quickly just to give you a little bit of background. This is an example of what a gravity offload rig might look like, similar to ours. This is the pulley, which maintains a constant force on the cable, which is the offload force for the rover. This center of gravity. Yes. Thanks. The pulley has to stay on top of the center of gravity of the rover, which is where the visual tracking comes in, because you have to know where the center of gravity is. Okay. This is that similar image you've seen with the fiducial setup on the robot arm, where the fiducials are placed in that manner. And this is the flow of the experiment. You take a picture with the camera of the robot arm, you send that picture to the fiducial tracking code, and it spits out the pixel location of hopefully all 5 fiducials. And then you run that through motion estimation code, and out pops a position estimate. And you calculate the distance from your position estimate to the actual position that you got from the robot at the instant the frame was taken. And that distance is the error in your estimation. Some more notes about the setup. The distance from the camera to the robot was around 3 meters, and the robot arm was moving around 10 millimeters per second. And the reason that's so slow is because if it was moving any faster, the fiducials in the image the camera took would be too blurry to be recognized. Before I move forward and explain the error, I just want to make it clear that this position estimate that we have is X, Y, and Z position. But for the application of gravity offload, you only care where the center of gravity is in the horizontal plane, because you want to be above the center of gravity. You don't have to necessarily be at the center of gravity. So you can throw away Z. So when we calculate the error, we threw away Z, and you just calculate the X and Y distance. So perhaps a better name for this project, instead of visual tracking, would be planar visual tracking, or planar optical tracking. So the error, the maximum error was 2.5 centimeters, the average was 1 centimeter, and the minimum was a millimeter. Here it is in graph form. It's two-dimensional error in X and Y, as I've explained. Error versus frame. Each frame the camera took, we calculated a position and got an error estimate for it. You can kind of think of the frame axis as time, because the frame rate was relatively constant. It was a little bit more than 2 frames per second. And that looks to be about 225 frames, which is close to 2 minutes this was running for. The requirements for the error had to be within 5% of the distance from the camera to the robot. And in this case, that number was 3 meters. So the maximum error, 2.5 centimeters over 3 meters, is 0.8%, which is good. Next steps are to clean up the code, make it more readable, so the next person who's working on it doesn't pull their hair out. Plug up memory leaks. A memory leak is, in case you don't know, a place where your program allocates memory and then doesn't deallocate it when it's not using it, so you keep on wasting memory. And this keeps on happening until you use up all the memory and the program crashes. So fix that. Then I want to rerun the test to see if you can change some camera settings so that the robot arm is able to move faster without getting the